Hello everyone, thank you for joining another Cyber Skyline Live. I'm Franz Payer with Cyber Skyline and I'm here to help you learn cybersecurity. We run these episodes for you, so please stick to the end and vote in the poll for what you want in our next topics. And if you're participating in the National Cyber League, please remember that the preseason ends on Monday, the 18th, that's a couple days from now, and the individual game will start next Friday on October 22nd. This week's topic is reverse engineering a network protocol, and I'm going to jump into my slides, so please ask any questions along the way, and in the meantime, let us know where you're from. All right, so today we are taking a look at reverse engineering network protocol. What does this mean? Well, the big question that you're probably wondering first is, what is a network protocol? And simply put, network protocols are just like a standard way that computers communicate with each other over a network, right? So it's important that it's standardized because if one computer is sending data in a different format or in a different sequence, then it becomes difficult or impossible for the other computer to understand what's happening, what the communication's about. And so there are specifications which dictate how do computers communicate with each other. And these specifications dictate different network protocols. And there are network protocols for HTTP. You can see some examples I provided here. Chrome, Firefox, Safari, they all support HTTP, which is the Hypertext Transfer Protocol, as well as the HTTPS protocol, the secure version of HTTP. And because they all understand this protocol, they all know how to talk to each other, they're all compatible with each other. So that's why there are different browsers which somehow still work with different web servers. And if you're familiar with different web servers, there's Apache, there's Node.js, there's Microsoft IIS, there's a bunch of different web servers out there. And they all still work with these different browsers. And the reason why they're intercompatible is because they all understand the HTTP and the HTTPS protocol. Likewise, I give another two examples here, Microsoft Outlook and Apple Mail. They both support POP3, which is one of the protocols used for email communication. And that's why they will work with any POP3 email servers out there. These standardized protocols are so critical, so important to allowing different software applications to talk to each other over the internet. And another thing to keep in mind here with these protocols is that, I give the examples of HTTP and POP3. These are public protocols or open protocols. Basically, the organization that created these protocols, they create a document that says how the protocol works and they publish it online. So anyone can understand how the protocol works and they can create their own application that will be compatible and work with that protocol. There are some companies who create their own proprietary protocol. And so they don't tell people how the protocol works. They don't publish it online. Only they can make applications, only they can make software that will work with their own with their protocol. This is very typical, I think, in video games. You might have a lot of video games where they have like an online component to the video game, and they don't see a need to publish how the protocol works because only they should be writing software that works with their protocol, right? And this is typically something they'll do to prevent people from like cheating. They will intentionally obscure and not tell people what that protocol is, because if people know how the protocol works, then they could cheat, right? They can, if the data in the protocol is sharing, let's just say coordinates of where someone is on the map, right? Then if you can look at the protocol, then you can easily figure out where everyone is on the map, right? So we typically see that like video games, they don't have public protocols. If you want to learn more about networking and learn more about network protocols, I would definitely recommend checking out on our blog page, trove.cyberskyline.com. We have some resources there to help you understand and learn how computer networking works. But now that we understand what a network protocol does, where can you find network protocols? And the very quick and simple answer is Google it. And let me show you here. I did a quick Google search for HTTP protocol spec Spec is shorthand for specification. And you can actually see the very top item here, RFC 2616. And RFC stands for request for comment. Typically, a lot of these open protocols, they will create a draft of how they want their protocol to be defined. And then they will put out what is called a request for comment. And they'll ask the public, hey, what do you think about my protocol? Do you think there's issues with it? Would you do things differently? And then after they get feedback from the public, they'll standardize it and say, okay, this is no longer a draft. This is the final version. And this is what we're seeing here is one of those RFCs. So if you actually click on that, it will generate a massive text document. And you could see versions of these which are a little bit prettier, not just text. But like this is, last I checked, it was like a 90-some page document on how HTTP works. And it goes through everything, right? It tells you like what are the different terms that are being used, what's the format for a request, what's the format for a response, how do the headers work, how does the data get encoded, like all of those different things. Those are in the specification. This is not a light reading. If you're going to go through a specification like HTTP, it's a very sophisticated protocol. Most protocols out there are rather challenging. The reason why you would want to read a specification like this, one of two reasons. A, you are a developer and you want to build some new browser, let's just say as an example. You want to build a new browser and you want to make sure that it works with HTTP servers. So you need to read the HTTP specification so that you can tell your browser, you can write the code for your browser that tells your browser when you send a request to a website, what does that request look like? How do you define that request? And then when you get the response back from the website, how do you read the response? How do you interpret it? How do you make sure that you understand how do I actually go about and display the web page? Because what's happening is the server is sending your browser the data. It's your responsibility as the developer of the browser to figure out how do I take that data and make it look nice and make sure that I'm displaying the contents of that information to my customers, right? So that's one reason why you might want to read a specification. Another reason might be because you want to analyze some network traffic, right? You see two computers communicating with each other over the network. And if you don't have the specification, it's kind of challenging to understand what it means because you're guessing. You might be able, maybe you have the software and then you can perform some actions on the software and see what data goes across the network as a result of those actions. And then looking at the data, you can make educated guesses as to what parts of the data define different behaviors and different values, right? So let's just say you click on a button. When you click on a button, it does something. It sends a request over the network. You look at that request and you can say, okay, this request was generated when I clicked on this button. Therefore, this request must have all of the data associated with this button click. And then you can start guessing, well, maybe this part of the request specifies which button I pressed, and maybe this part of the request specifies who I'm logged in as, so forth, right? It's very, very challenging. It's a lot of guesswork, and it's very hard to go from no knowledge of how the protocol works to understanding how the protocol works just based on some behavior. If you're lucky enough and you're able to get hold of a specification, it makes it much, much easier for you to understand how does this protocol work, because it'll say, hey, the first 4 bytes in the request will define what button someone pressed, right? And then you don't have to guess that anymore because it says, okay, first 4 bytes refers to this button press. And then now you know, okay, when I click on this button, I see the request go through, the first 4 bytes refer to that button. So if I wanted to say automate pressing that button, I could create a program which just sends a duplicate of that request, right? And so these are all kind of like reasons why you'd want to like reverse engineer a protocol, and the specification really, really helps with that process. So either you want to create some software that works with that protocol, or maybe you want to understand what is happening over the network, right? Trying to understand what that data is. What is it that these two computers are saying to each other? So those are specifications. Now, today we're going to be doing the Pandora challenge, which is in the network traffic analysis section in the gym. This has a predefined specification that we provided to everyone. So if you're doing NCL, you can follow along. It's in the gym. Go to network traffic analysis and you'll see the specification here on the left side. You can expand the window, make it a little bit bigger. And I'm just going to dive through the specification and break it down, bit by bit. How does this actually work? So I'm just blowing up right now the overview section here so we can read through this. And what the overview section says is communication between the client and the server will contain three types of messages: an initialization, an encrypt request, and encrypt response. The connection is started with the client sending an initialization message, which contains the number of encrypt requests that the client wishes to make. Then the server will send the length of its response. Then the client sends their encrypt requests to the server. And then after all the encrypt requests have been received, the server will finish sending a single encrypt response, which contains the hashes of all of the data that was sent by the client. So this is specifically saying what is happening in this communication. It doesn't actually say what the server is doing other than the fact that it sends back a hash. If I had to guess, well, I created it, but if I had to guess as a normal user going through this, I would say that what seems to be happening here is that a client will send some data to the server will encrypt that data, maybe it'll store that data, and then it'll send back hash responses so that the client knows that the data was saved, and maybe if it wants to refer to that data again and get the data back, maybe it sends the hash to get the data back. That's kind of like my guess as to what this protocol is actually like doing, like what's the purpose of sending this data. But it sounds like there's multiple components to this communication, and you can break this down even further and make it a little bit simpler here. And it's 4 stages. The first stage is that the client will tell the server how many requests it's making. And then after that happens, the server will say, okay, based on what you told me, I'm telling you now how long my response is going to be, right? So when I give you my response, it's going to be this length, I guess in bytes. After that, the client will send its requests to encrypt this data to the server. And then after the client sends all of those requests, the server will send back all of those hashes as a response. So those are the 4 steps that are happening here. We're also given more technical specifications as to what the initialization message, these encrypt requests, and these encrypt responses look like. And so the initialization is specifically a 4-byte integer, and it says in network byte order. What network byte order means is that it means that, it's a 4-byte integer, so we have 4 bytes. Network byte order means that you're reading left to right. There's also, it's referred to as big endian, which means that you read left to right. There's also little endian, which means you read the other way. You read from right to left. And so the specific order kind of matters here, right? Because obviously, if the number is, for example, 001, there's a very big difference reading left to right versus right to left. If you read it left to right, 001 is just 1. If you read it the other way, you read it right to left, the number is now 100, which is 100, right? So the order in which you read these numbers matters. Typically, for most network communications, you will often see the data being stored as this network byte order, which is the big endian, which means that you read left to right. So that's just, if you're an English speaker, it's pretty straightforward. That's how we normally read. Some other languages, they read back the other way. They read from right to left. So just keep that in mind. If you have some funkiness with trying to like extract the number from the data, make sure that you're reading it in the correct direction. So that's the initialization, right? It just tells you how many requests are going to be sent. And then these encrypt requests, there's three components to the encrypt request. The first component is this check. It's a fixed 2-byte integer, and an integer is just a non-decimal number. For those of you who need a little bit of a math refresher, it's 2 bytes, and it's in network byte order, and it verifies the integrity of the message. So my impression of this is either some sort of checksum or some sort of magic value, which stays constant, so that we know that everything that follows is going to be part of this encrypt request. There's also the second component, which is len or length. This is a 4-byte integer. So it's a fixed 4-byte integer that says how long the data is going to be. So you have a field which says how long the rest is going to be. Now, the reason why you would need to have this field here to specify the length is because the data could be a variable length. The data could be 100 bytes long, it could be 1,000 bytes long, it could be 1,000,000 bytes long. And if there isn't an indication for how long it's going to be, what happens if there's something after that data? Let's just say there's a second request that follows. It's important that the recipient of this data knows the length of the data, because otherwise it won't know where one request ends and one starts and one ends. Because if for whatever reason it's variable length and they just keep reading, they don't know when to stop. And so the program would just assume it keeps going. And that's why it's important for there to be some sort of indication for any of these variable length fields, that prior to the variable length field, there's some sort of indication for how long that variable length field is. Otherwise, the person reading the data will have no idea when to stop the field. All right, and then the final component here is the encrypt response. So the server will first send back a count, which is the length of the data in bytes that follows. So it's going to be it's a variable length. It's going to say how much data is going to be sent, and the data that follows it are these hashes. And that's part 2 here. It says the encrypted hash is requested by the client. Each hash is in the form of a fixed length chunk, and these hashes are in the same order that the request was made. And so basically, if in theory what would happen is the value of count would be the number of hashes, that's the n at the top in the initialization, n times the length of each hash, right? Because the server is going to send back an encrypt response, which will contain hashes for all of those requests. And each hash is the same length. So the length of all of the hashes together is simply the length of each hash times the number of hashes that there are. And we're going to see this when we look at the actual data. Before I move on to the next slide, I'm going to answer some questions in the chat here. So Kyle is asking, another thing to look at that aren't part of the specification, is this TCP or UDP? What port? How does this connection get set up? Those are very good questions. They are not in the specification. So these are things that you would need to find out by yourself. Some specifications, if they want to provide that detail, will say this is TCP or this is UDP. Sometimes the specification might support both. Maybe it supports only one or the other. There's also something that you need to worry about, which is the quality of the specifications. You need to keep in mind that the people writing these specifications, oftentimes they're human. I mean, all the times they're human, so they can make mistakes. They might make a mistake in the specification, and you might find that mistake when you're reading the specification. And that's just how it is, right? You're like, what are you gonna do? You just have to deal with it. Sometimes they make a mistake. It gives you a headache because you start having problems because they made a mistake in how they wrote the specification, and you might need to contact the author to get clarification if you identify a mistake. But a lot of these specifications are being written by people who are often doing this as volunteer effort. They're unpaid. This is on their spare time. It's prone to mistakes. Um, just keep that in mind that you know, don't take the specification like take the specification at face value. Someone wrote a definition for a recipe for how they did it. Think of it as a recipe, right? They might have made a mistake in the recipe. And so sometimes you need to be able to distinguish, am I making a mistake here, or is it possible that the recipe is incorrect, that the specification is incorrect? Most of the time, you probably made the mistake, and most of the time, the specification is correct. But there's a slim chance, and I'm just telling you, take it at face value. So, yeah, keep that in mind. Kyle's also asking, actually, let me see here. Okay, Kevin's asking, I thought 100 was 4. That's the 100. This is something that you need to, if you are assuming that 100 is in binary, then it is 4. If you're assuming 100 is in decimal, then it's 100. If you're assuming it's in hex, it's 200 and 200 no, it's 100 and I forget what it is. Whatever it is in hex, right? You need to understand the number value that you're looking at. How is it encoded? What's the base of that number? Because numbers can be converted, they can be encoded, they can be translated. If you don't know what the base is, you actually cannot determine the value. You can only guess at the value, right? And so 100 could be 100 in decimal. It could be 8 it could be 4 in binary. It could be a different number in octal. You need to know the base. And hopefully that's specified in the specification. By default, you can kind of assume well, you need to assume what data you're working with. Most of the time you're working with raw data, which means that it's your responsibility to understand how that data is being represented. If you're printing the raw data as binary, then that data is in binary. If you're printing that raw data in hexadecimal, then that raw data is in hexadecimal. You could print it out in ASCII, and then therefore the data is now in ASCII. You choose what format you want to put it in. All right, so with that, I'm going to jump into the actual data here. And the way that you get this data is that we're looking at a packet capture. And so you have this as a .pcap. You can open it in Wireshark. And what you want to do is first filter out any unrelated data. The way I would recommend doing this for this gym challenge is that if Wireshark is telling you that this is HTTP traffic, this is SSH traffic, this is DNS traffic, this is whatever traffic, if Wireshark knows what type of traffic it is, you can omit it, right? Because we're talking about a custom protocol. And so if Wireshark knows the protocol, then that can't be what we're looking for, right? Because by virtue of the fact that this is a custom protocol, Wireshark should not be able to identify it. That will help us narrow down the data. And this is one of the hard parts of the challenge, is actually finding out which part of this packet capture we want to be looking at. Once you identify the data that we're looking at, that we're interested in, you're going to right click on one of the packets, and then you're going to select follow and then TCP stream. This will give you all of the data in the communication back and forth between the server and the client. And it's going to omit all of the protocols that are all of the lower layer protocols. So you're just going to get the raw application data, all of the TCP IP data, the hardware level, the route level data, like all of that data is going to be omitted. It's going to make your job a lot easier to dissect this information. And then from there, you want to make sure that you're viewing this in the correct format. I mentioned before, you can look at something as binary data, hexadecimal data, ASCII data even. In this case, what we want to do is select the raw option. This is going to display the data as hexadecimal, but unlike the hexadecimal option, it will not try to format the data into columns. Raw leaves the data as is. It won't try to format it, but it's still going to be displayed as hexadecimal. The difference is that it will not try to put it in a column format because we don't want it in a column format. That'll actually confuse us a little bit more if it is. All right, so I'm going to show you what this looks like. And if you follow those steps, you're going to get this window. At the end of the slides, I will do a demo and I'll show you how to actually get here. But for right now, I'm just going to walk through analyzing this data as is. So I need to move my my display over here. I'm going to move myself to the bottom right. And we're going to break this down. You can see here that we have some red data and some blue data. The red data is the data that the client is sending to the server. You know that it is the client because the client reaches out to the server first. And so the first data here being red tells us that this is the client that is making the request, which leaves the blue data as the server data. And what I'm doing is I'm going to highlight in yellow the component that we're looking at, because we're going to go like step by step. And so I'm only going to highlight the step that I'm looking at. And at the very top right, I'm going to reference the part of the specification that is relevant for us understanding the data that I've highlighted. And so if you recall from this, the specification, it said that the client will connect to the server and then send a 4-byte integer, which will indicate how many requests that it is going to make. And so you can see here, we've got a 4-byte integer. Keep in mind that in hexadecimal, 1 byte is represented as 2 characters. And so that is why when we have a 4-byte integer, we are seeing 8 characters, right? It's these 7 zeros and the 1 5 here. So this data is in hexadecimal. I'm showing it here as 0x000005. And when we convert hexadecimal into decimal, this means that there are 5 requests from the client. As it turns out, you know, hexadecimal 05 is the same thing as decimal 5. So that's pretty straightforward. So we know now 5 requests are coming from the client and going to the server. Now, the next step that happens is the client is starting to go and like send the data to the server. And so this next component is that 2-byte check in the beginning of the request. And so over here it says the check is a fixed 2-byte integer in network byte order that verifies the integrity of the message. And so we know, just based on what this says, 2 bytes, that's 4 characters, that's the 0417. That represents the check value for the first request. What follows next is the server is now responding to the fact that the client connected and said, hey, I'm sending 5 requests. And the server is saying, okay, you sent 5 requests. I'm going to give you a 4-byte integer that will tell you how long my response will be. And right now we are looking at this 4-byte integer value being 0000000A0. That's in hexadecimal format because we selected the raw display. If you convert this A0 from hexadecimal into decimal, you'll get a value of 106 in decimal. So because I mentioned that, wait, hold on a second. Let me make sure I did my math right. Yeah, okay, I did my math right. So because I mentioned that each hash is the same length, and we know there are going to be 5 requests, which will return 5 hashes. If we take 106 and divide it by 5, we get 32, which means that each hash is going to be 32 bytes long. So we know that now. And let's move on to the next step. The next step here is part two of the encrypt request. So what's actually happening is that like the server and the client, they're like talking to each other at the same time. It's not like the client like talks to the server, sends all of the data, and then waits for the server to respond. The client is sending data to the server, and the server is like responding halfway through the client's communication. And it's responding as soon as it's ready to respond. So this is a little bit different than like if you had a conversation with someone. Normally you would talk, and then they would talk, and then you would talk. The server is being like very, very proactive, and as soon as it finds out how many requests the client is making, it knows, oh, well, obviously my response is going to be 160 bytes. So I'm going to tell you it's 160 bytes right now. Even though it could, in theory, wait a little bit to actually get those requests before it actually gives its response, right? So that's why this data looks like it's a little bit out of order. You would normally expect the client to finish its request before the server starts responding, but because these are computers and they can like interweave their communication like this, and they understand it without any problem. But you, as the human reading it, you need to understand that this blue here was the server responding early, while the client is still sending its requests. So with that in mind, the second part of the encrypt request is this length. This is a 4-byte integer that says how long the data will be. And in this case, it is 0x58, which if you convert hexadecimal 0x58 into decimal, you will get 88, which means that the data in this request is going to be 88 bytes long. So then I highlight 88 bytes, and this is the data to be encrypted in the first request. So 88 bytes, that's all of it over here, which means that the next thing that follows will be the second request. So we're going to start this step 1, 2, and 3 from scratch in the encrypt request. We are going to have the check. This is the 0417. And so now you can see that 0147 is the same for every single request. So this helps us know that we did it right, because if we got a value that was different than 0417, it's probably an indication that maybe we took too many or too few characters in the data portion. After the check, we have the length. This length is different. The previous one was 0x58. This one is now 0x48. So it's a different length. And in this case, the length is 72 bytes long instead of 88 bytes long. So we have a different length request. And then that must mean afterwards is the 72 bytes of actual data in that second request. And so there are 5 requests in here for the sake of time. I'm not going to go through every single one individually. And so I'm just going to say the remainder here in the data that the client sent is going to be request number 3, request number 4, request number 5. As an exercise for you as the viewer, you can go through this data, especially if you have access to the gym and you go do the follow TCP stream, you get all this text. You can continue doing what I did, right? Take the first 2 bytes, that's the check. Take the next 4 bytes, that's the length. Then grab the length, that's the next request. Keep doing that, and you should be able to do that for the remaining 3 requests here. But this is now the end of the requests that the client sent. So now the server needs to respond, right? As per the specification. So the server response, part 1 was the server saying how long all of its hashes were going to be. That was the blue thing at the top here, this 0000A0, right? That's the length. Now we actually have the hashes. So there should be 5 hashes. We did the math already. We found out that each hash should be 32 bytes long. And so that's what I'm showing you here. This is 32 bytes. That's what's highlighted in yellow. So that is the 32 byte hash for the first request, which means that the next 32 bytes will be the 32 byte hash for the second request. and so on, right? Everything else remaining here, these are going to be the hash requests for request number, the hashes for requests number 3, 4, and 5. And that takes us to the end of the communication. So we've identified from the specification, we figured out, how many requests are being sent, how long each request is. We were able to identify uniquely each individual hash in the response. So we fully understand this protocol now. So all that is left is to go through and actually walk through the demo and show you how to do this using Wireshark so you can understand this. So I will switch over to my virtual machine, but if you have any questions, please ask them now. As I'm getting started, as I'm getting set up, I'll answer your questions. All right, so I'm here in the gym, the NCL gym, and um, I don't know. This is a little bit confusing sometimes, but there's actually a download option that's like hidden behind this window. I think uh, you can also download directly from here in CloudShark, but you could, in theory, solve this challenge using CloudShark. It's a little bit more cumbersome, but you could do it. I'm going to download the packet capture, open it in Wireshark, and we're going to solve it here. So before I do that, I'm going to answer some questions. It doesn't look like there are any. Kyle's saying, the fact that the server knew how long the response would be before the actual request means that the server knows how long the hashes it would produce were going to be in advance. Yes, that is correct. And part of like the definition of a hash is that it has a fixed length. So it's not just that like the server knew in this instance like all hashes should be the same length. So that's a very trivial thing for the server to figure out. All right, cool. So let's jump into it. If you will recall from my slides, and let me actually, I have a copy over here. The way that I suggested going about getting the data is that you want to filter out all of the data that is just noise, right? We want to figure out how to get this protocol that is being described to us in the packet capture. And so off the bat, I can see, okay, there's SSH traffic in this packet capture. SSH is, for one, it's encrypted traffic, and secondly, it's a known protocol, right? So let's take out SSH traffic, and that will help us narrow down our options. And so what I'm going to do is I'm going to say not TCP port, and what's the port? TCP SSH port. I'm just going to do a quick Google search because I forget. It's port 22. So I will say, okay, we want to filter out port 22. No more port 22. There are all of these pings here, these ICMP pings. So let's get rid of those and not ICMP. All right, we got rid of ICMP. All right, there's DNS data here. We don't want DNS. So let's say not TCP port. And I remember that DNS runs on port 53. So I'm going to take that out. And is it not port 53? DNS port. Oh, no. My problem is that this DNS is running on UDP. So I need to do UDP port 53. And there's some HTTP traffic in here. Let's take that out as well. So and not TCP port equals 80. Because HTTP runs on port 80. All right. So now we've kind of narrowed it down. I can actually see all of the remaining results pretty easily on this window here, right? This is everything that's left. It's not much. So what we're left with is ARP, which is another protocol that's defined, and we don't need to know about it. We don't need to worry about it. And we have all this TCP traffic. Now, typically, the network protocols that you're going to be interacting with, these application specific protocols will either be running on TCP or UDP. So the fact that we're seeing TCP traffic here that Wireshark is not able to interpret any further is an indication that this is probably where we want to be looking. And so what we can do here is right click, and I said follow, and then TCP stream. And so here's all of that data. Now, by default, Wireshark is going to try to display the data as ASCII. This data is not ASCII, right? If you look at the protocol, it's specifically identifying integer values and raw data. So there's like no guarantee that any of this is going to be ASCII printable. And if you look at it, it looks like gibberish. So what we're going to do is going to go over here and we're going to say raw. This gives us all of the data as hexadecimal without any formatting. If you go here, you do hex dump, you can see it tries to do some formatting. We don't want the formatting. We want to do raw. But hex dump and raw will both give you the data as hexadecimal. And now you can see these are the values that we got. This we got in the slides. So this 5 is a number. And this represents all of these characters here. This represents the number 5 because it is a 4-byte integer, which is represented as 8 characters. And this is the equivalent of, this, like the reason why there are all these zeros here is because it needs to be a fixed length. It needs to be 4 bytes. So if you only need one character to display your value, you need to fill all those other spaces up with zeros. So that's why there's all these preceding zeros, is because it needs to be a 4-byte integer. So this is the 5 requests. This is the identifier, the check in the request. This is the server saying that there's 160 bytes, I believe, in the response. All the way here, this is another 4 bytes, which represents the length of the request of the first request's data, right? There isn't really an easy way to like from here for me to go and get the length, the actual contents of the data. I did that offline because I didn't want to show you how to do it. I didn't want to like waste your time doing it live because that's just counting, right? But here's everything that you needed to do to analyze the data. You can copy this and put it in a notepad. You can put it in a spreadsheet. You can put it in Word, whatever makes the most sense for you. But once you get the data, the raw data, you can then follow the guide step by step, the specification, right? You be the computer program, you read 4 bytes, and then after the 4 bytes is this, and then after that is this, right? You're just following it step by step. As a bonus, I will actually try and solve a couple of these questions here. So we're being asked, what is the IP address of the server? So let's go back and we can look here and you can see that, remember, right? The very first request is being made by the client. The client reaches out to the server. And so the source of the first request is going to easily tell us that this is the client. And then the other one must be the server. So the other one, the destination being a server, that's 10.1.0.20. 10.1.0.20. Cool. And then this source here is the client. 10.1.0.217. So we've got all of those. What port is the server listening on? We can figure that out by looking in this info column. Another way that you can do it is if you look at the TCP window here, you can see source port and destination port. So the source port is the port that the client is making the request from on their computer, and the destination port is the port that the connection is being sent to on the server. So this looks like 60123. 60123. Sorry, my head is covering all of these, isn't it? I'll move myself back. to the top over here. All right, so that is the IP address of the server, the IP address of the client, the IP address, the port of the server. What is the magic 2-byte decimal, 2-byte ID in decimal? Well, we already figured that out during the slides stage. This was the 0417. 0417. What is the magic 2-byte ID? Do I need to, what did I mess up here? All right, I just had to put it in hexadecimal format. OX 014. And then how many encryption requests were made by the client? So this was the first line here, right? When the client connected, it said how many requests it was making, and in this case, it is 5. So 5 requests were made, and then the length of the first encrypt request. I'm just going back to the slides here. The length of the first encrypt request, 88 bytes. 88. The length of the second one is 72. How large is the individual encrypt hash in bytes? We went over that. That's the 160 divided by the 5, so that's 32. And then what is the encrypt response in hexadecimal form of the first request? So that would be this value, and I don't think I can copy and paste very easily from the slides here right now. So it's whatever that value is. And then for the second request, the second hexadecimal hash, that would be this value here. And for the final question, what is the hidden flag being sent over the protocol? So what I would recommend doing with this is playing around with looking at the data here. What my gut feeling would be is that this data, if there's a hidden flag in here, it has to be in that data field, right? Because that hash is going to be a hash. It shouldn't have any substance for us to work with. And because we're saying hidden flag, that means it's in a specific format, right? So we need to find a way for that format to be added, which means that somewhere in these requests in the data, there must be this hidden flag. And I'm going to actually go back to the original ASCII, because if you look at this, you might see something, you might see some sort of pattern, and this requires a little bit more experience. This is like a little bit of a harder challenge, because what I am seeing here is when I'm looking at these red characters, I can tell that these characters are part of the base 64 character set. These are all base 64 characters. So what I can do is I can actually copy just this red component, because that has all the requests, and I can put it into a base 64 decoder. And if I do that, you can actually see here NCL-FJCG-1632. So this is the flag format, right? The 3 digits dash, and then the 3 characters dash, the 4 characters dash, the 1632. So this is actually an older flag that we had back before we changed all the flag formats to use SKY at the beginning. But this is a flag, and so you can take this and submit it over here. And that is the hidden flag. So we went through all the different parts of solving Pandora. Hopefully that was helpful. I'm going to stick around and answer some questions. So if you have any other questions, please ask us right now. And I'm going to open the poll. Now we try to pick topics that people are asking for in the polls. And if you have any other ideas, ask them in the chat. But let us know what other topics you want us to cover. Next week's topic, next week we're going to be covering ICMP pings, and it will be on Tuesday, because individual game is starting up on next Friday. we want to leave a little bit of buffer there. So we will be doing our crowdcast on pings on Tuesday, same time, 5 p.m. Eastern. And while we got the poll running, please ask any questions you have, and I'll get to them. So, got a question. Is there a packet that we can find CPU information of the computer? Not in this data. And I think you're probably asking a question that's from a different, I think you're asking a question that's from the preseason here, because there's a question in the preseason that asks for the CPU information of a packet capture. There isn't a predefined portion in the packet that will tell you CPU information. However, the protocol in the packet capture may have some information. Maybe the protocol sends some CPU information in the network traffic. So that's something that you should look for if you're trying to solve that challenge. All right, let's see here. We got a question asking, how do we get to the point where we pull the data in base64 format? Sure. So if you go to Wireshark and you have the follow TCP stream up here, if you switch back from the raw view to the ASCII view, ASCII is just the text readable format. You can see all of the data attempting to be encoded and interpreted as ASCII values, so character values. It so happens that this data component has base64 data encoded as ASCII. So basically what that means is it took some values, base64 encoded it, and then saved it as ASCII. And so when we do the show as ASCII data, we can look at the base64, and then from there, we can take the base64 and decode it. And then we have another question here. What is the best way to find WEP in the packet? So if you are looking at a WEP packet, you'll be able to see that as one of these lower layers. And so when data is sent over a network, over the internet, there are multiple different layers, and this is explained in Trove. And so if you haven't checked out Trove, trove.cyberskyline.com, we have this section here, the computer fundamentals for cybersecurity. There's a section on networking, and it talks about these different layers. So WEP is part of Wi-Fi, and Wi-Fi is part of this link layer protocol in the packet capture. And so you will see it there. Now, this packet capture was not sent over Wi-Fi, so you're not going to see any WEP. But if you look at a packet capture that has WEP data, and I can actually, just to answer this question here, if I download this packet capture of WEP data, whoops, and I click on one of these packets, I cheated here. I already cracked this packet capture, so I already have all of the I already have it decoding, so I need to take this one here. Well, I didn't crack this one yet. So you can see all of this you can see all of this data here, and there's this IEEE 802.11. This is where the Wi-Fi data is, and then there's a section here for WEP. And so you can actually see the IV for the WEP here. So you can find it in specifically the this lower level layer protocol, but you need to be looking at Wi-Fi traffic or you won't find it. And the Wi-Fi network needs to be using WEP for security and not something else. And then I see some questions here about like the way that the answer should be submitted. I agree with you all. I think that is a mistake that we made in the wording of the question. So after this episode, I'm going to go through and update to accept both a decimal format and a hexadecimal format. So you don't have issues submitting your answer there. Um, All right. So I think that covers everything then. Thank you all for joining us today. Remember that if you're doing the National Cyber League, preseason ends on Monday, and on Friday, we have individual games starting. Don't miss that out. Get your scouting report. Individual games where all the fun magic happens. Then after individual game, we got team game 2 weeks later. So a lot of interesting, exciting things coming up. Thanks for voting on the poll. If you have any last minute suggestions for ideas for us to cover, please post it in the chat. I don't want to run out of ideas, and I want to know what you all want to learn about. So we'll cover additional protocols and different topics in the future. Next week, we're going to do ICMP, and that will be on Tuesday, 5 p.m. Eastern. You can actually, if you're watching this on Crowdcast, you can go to our page and you can look at all of our upcoming events, and you can register for that right now. But with that, thank you for joining us, and we'll see you next week. Take care.